Welcome along. So you're revising for your GCSE Physics exam. Let's get you completely up to speed on changes of state and the particle model. This is a huge topic, but we're going to break it down so it's super clear. Right, let's kick things off with something you see every single day. You know, solids, liquids, and gases. You've seen ice melt, you've seen water boil, but for the exam, you've got to explain why. Understanding the physics behind all this everyday stuff, well, that's where you're going to pick up some serious marks. So, how do we explain it all? Well, luckily, there's one single powerful idea that holds the key to everything. It's called the particle model. Get your head around this, and the rest just clicks into place. And here it is, the big idea. It's this simple. Everything, and I mean everything, the desk you're sitting at, the water you drink, the air you're breathing, is made of tiny, tiny particles. And these particles are never, ever still. They're always moving. How they're arranged and how they move, that's what makes a solid, and a liquid, a liquid. This table sums it up perfectly. So, in a solid, picture all the particles locked into this neat, regular pattern. They're held so tightly together they can't go anywhere. They just vibrate on the spot. That's why a solid keeps its shape. Now, with a liquid, the particles have a bit more energy. They can break out of that rigid structure. They're still packed in close, but now they can slide right past each other. And that's exactly why liquids can flow. Then you've got gases. Here, the particles have loads of energy. They're zooming all over the place, really far apart, just bouncing around and filling up whatever container they're in. Okay, so this particle model is also brilliant for explaining another really key concept in physics: density. You know, that feeling of why a tiny pebble feels way heavier than a massive balloon? It's all about the particles. First up, here's the official definition you need to learn. Density is the mass of a substance per unit volume. Or, to put it another way, it's a measure of how much stuff you can cram into a certain amount of space. It's all about how compact it is. And this is the formula you absolutely have to know. No excuses. You need to be able to remember it and use it. Density, that's the funny piece symbol called rho, is just mass divided by volume. Seriously, get this one memorized. It's almost guaranteed to come up. And see how this ties straight back to our particle model? Imagine you've got a box. If you fill it with a solid, the particles are all jammed in together, right? You can fit loads of them in. But if you fill that same box with a gas, the particles are all spread out. So more particles in the same space means more mass, and that means a higher density. Simple as that. You'll also need to know how to actually measure this in the lab. For a weirdly shaped object like a little rock or something, you first pop it on a balance to get its mass. Easy. To get the volume, you use a displacement can. You fill it with water right up to the spout, then carefully lower your object in. The water that spills out into a measuring cylinder, that's your volume. Then you just do mass divided by volume, and boom, you've got the density. This is a really common required practical, so make sure you know the method inside out. Okay, next up. We know about the different states, but what's actually going on with the particles when something like ice melts? And, really importantly, what happens to the total amount of stuff when it changes? Right, let's take melting. When you heat a solid, you're just giving energy to its particles. They start vibrating more and more like crazy until they've got enough energy to break the bonds holding them in place. They break free and start to slide past each other. And just like that, the solid has turned into a liquid. But, and this is the crucial part, the particles themselves are exactly the same. They've just been rearranged. Because the particles haven't changed, this whole process is what we call a physical change. That means it's reversible. You can get it back to how it was. If you cool the liquid down again and take that energy away, the particles will slow down, lock back into their pattern, and you've got your solid back. This leads us to a really, really important rule in physics. It's a big one. When a substance changes state, whether it's melting, freezing, boiling, whatever, the total mass you have at the end is exactly the same as the mass you started with. Mass is conserved. It doesn't just disappear. And why is mass conserved? Well, our particle model explains it perfectly. We didn't add any new particles. We didn't take any away. All we did was change how they were arranged and how much energy they had. So if you start with a block of ice that weighs 100 grams, once it's melted, you will have exactly 100 grams of water. It has to, because it's still the same number of particles.
All right, let's wrap this up and pull everything together. This next bit is your key exam takeaway summary. If you're cramming for your revision, this is the slide you really need to burn into your brain.
So here we go, the 5 absolute must-knows. 1. The properties of solids, liquids, and gases. It's all about how their particles are arranged and how they're moving. 2. You have to know what density is, and you have to know that formula. Density equals mass over volume. 3. You need to be able to explain why solids are denser than gases using the particle model. It's all about how tightly packed they are. 4. Changes of state are physical changes, which means you can reverse them. And 5, the big one, mass is always conserved because you're not losing or gaining any particles. If you can lock those 5 points down, you're going to be in fantastic shape for the exam. So, to finish off, I'm going to leave you with a little something to think about. When ice is melting, you can keep heating it, but its temperature stays stuck at 0 degrees until it's all melted. So if the energy you're adding isn't making the particles move faster and raising the temperature, where on earth is that energy going? Ponder that one, because the answer leads us right into the next topics, internal energy and specific latent heat. Good luck with the revision.